as we get into calculus, we're going to see that there's a large component that involves trigonometry and also geometry. Now these are really important ideas. And what are they after? Well, if you look at these words, they have the common metry. And metry is measure. And so we're trying to measure things. And oftentimes what we're trying to do is understand some relationships. And one way to understand relationships is say, well, how does A compare to B? Look at it by a ratio. So A over B. Now, one of the nice things about ratios when it comes to geometrical objects is that ratios aren't changed by scaling. So they're somehow scaling invariant. And that's a very useful tool. And that's going to be one aspect. And then the other aspect that we're going to talk about is the Pythagorean theorem. And let's just go ahead and just state that really quickly. This is a really nice result. It says that if you happen to have a triangle, of course not just any kind of triangle, a right kind of triangle, and that you measure, see there's that metry, A, B, C. Those are the lengths of those three sides. Then, Pythagorean theorem says A squared plus B squared equals C squared. All right. And we're going to come back and talk about how we use the Pythagorean theorem. And for those of you who go to the end, we'll try to throw in a proof, maybe two proofs of the Pythagorean theorem. All right, so let's talk about scaling. So one of the ways that you see scaling showing up is this notion of similar triangles. So similar triangles is just a way of saying the angles match. And so what doesn't match is the size. I guess I should pause before we go much further. Why triangles? Why not build our understanding around rectangles or squares? And the nice thing about triangles is that if you pick up a triangle, this is a rigid shape. In other words, if you were to pick this triangle up and try to shake it really violently, it wouldn't change its shape. And put it back down, still the same shape. But if you did that with a square or a pentagon, they would sometimes morph and bend at the corners. But triangles are rigid. All right, so similar triangles. Here's an example of something that you might see, where you say, okay, I have two triangles, and maybe they're like this. So these two sides are parallel, which means, of course, that our angles are the same, and so that they are, up to scale, the same. So we can apply the fact that ratios are not changed by scaling to make some conclusions. For instance, suppose we know that the top here is, say, 6 units across, and maybe that the whole length from the top down to the tip at the bottom is 10. And suppose we know that this length here is y, and this length here is x. What can we say about y and x? Can they be arbitrary? And the answer is no. They have to depend on each other. So how do we figure it out? Well, what we do is we say, look, the ratios are not changed. So we look at ratios of lengths. 10 is to 6. So the height up and down to the width across at the top is the same as y is to x. And so we can conclude that y is 5/3 x, because we can simplify 10/6 to 5/3. So this is a nice way to use geometry. So if you have a problem involving triangles, and oftentimes when you have problems, triangles are very, very common, especially right triangles, but they don't have to be right triangles. And if you're trying to figure out how do lengths relate to each other, look for similar triangles and try to find relationships coming up there. All right, well, since we know that these ratios are not changed by the sizes of the triangles, that sort of leads to this idea of like, well, let's focus on studying these ratios in triangles. And of course, the question is, which triangles should we pick? Well, we don't want to pick the wrong triangles, so what we're going to do is we're going to pick the right triangles. All right, so in other words, I have a triangle, and it's a right angle in one corner. And, well, let's look at this angle. We'll call it an angle name. We usually use Greek letters for angles because Greeks were the ones who started looking into geometry. And, well, the Greeks were often prone to using Greek letters, so it's not too surprising. So what do we know? We know that the ratios are the same, so we're going to give names to ratios. And we're going to base it off of this angle. So what we want to do is label the sides in relationship to the angle. So we have an opposite side, an adjacent side, and the side, sort of the long side, we call it the hypotenuse. And what are our names? Well, we're going to call sine of theta, that'll be the ratio of the opposite side to the hypotenuse side, and cosine of theta, that's the adjacent side to the hypotenuse side. Now, if you're thinking, where does the co come from? Well, it turns out that this co is complementary. So in other words, it's a complementary angle. So if you were to look at from this corner, what's the sine? Well, it's the opposite now is what's currently called adjacent over hypotenuse. So, okay, so that's the name. The other two important ones we should know how to figure out. Tangent, that's the opposite over the adjacent. And finally, secant of theta, which is the hypotenuse over the adjacent. So these are the important ones. There's a couple of others, but almost always we'll restrict ourselves to using these. Now there's a couple of facts that we can see automatically. Well, what are they? Look at how tangent looks an awful lot like sine and cosine if we were to take out the hypotenuse. And in fact they are. So tangent of theta, that's equal to sine over cosine. And just take the ratios. You'll see that the hypotenuses cancel. And then secant of theta looks a lot like cosine theta, it's just turned over. And so we have secant of theta, that's 1 over cosine theta. All right, well that's good. So that gives us a way to rewrite 1 over cosine if we see that in terms of secant. Of course, we can also go vice versa. In fact, one of the things that's often true about trigonometry is that there are many ways to write things, because it turns out there are many ways to write things. And one of the challenges, or if you like, one of the fun things, is figuring out, okay, what's a way to rewrite this to make it more useful? And so we need to start building up a collection of really important trig identities. So let's do a nice one. So we go back to the Pythagorean theorem. So if I come here, what do we have? We have that the adjacent side squared plus the opposite side squared is equal to the hypotenuse side squared. Now we can rewrite this by doing some division. So suppose for a moment we divide everything by the hypotenuse squared. Then what we'd get is that the adjacent side over the hypotenuse squared plus the opposite side over the hypotenuse squared is equal to 1 squared. And we have names. So that's cosine squared theta plus sine squared theta equals 1. So what do we see? We see that this identity, really nice one, is really just an expression of the Pythagorean identity. Now, did we have to divide by the hypotenuse squared? And the answer is no. We could divide by, well, let's say, adjacent squared. And if we do that, we'll skip the intermediate steps, but we'd get 1. And here, opposite over adjacent squared, well, that's tangent squared. And then here, we'd have hypotenuse over adjacent squared, which is secant squared. So both of these are just ways of expressing the Pythagorean theorem. And these are really important. And in trigonometry, when it comes to calculus, there's really six facts that will carry you through. And this is 2 of the basic 6. When I say 6 facts, 6 identities. You should definitely still know these. I don't count these. These are basically, you should know those by heart. Definition. Got to get it done. Got to get it done. All right. Well, we should probably talk about some specific angles, which means it's probably time to talk a little bit about angles. So when we're measuring angles, there's 2 different ways people talk about angles. One of them is degrees. And for degrees, we say that 360 degrees is 1 revolution. So in other words, we turn all the way around if we go a complete 360. The other thing is radians. Now, 360, you might say, oh, well, that's totally natural, until you start to think, well, why 360? Well, probably it's a very convenient number, highly divisible, which means we can break it up in lots of ways. But it's kind of an arbitrary. So the goal was, well, let's make something that's sort of not so arbitrary. So let's think about the word radians, because that can help us remember how it works. You notice that it looks like radi, or like, what other word? It's like radius. And in fact, that's the idea. It's a radius. And if you think about it in terms of a circle, let's draw a circle here. And I suppose this is one of our radiuses, r. And I start here, and I just start putting down the radius as I move around. So let's see, there's 1, 2, 3, 4, 5, 6, and I just a little bit short. 6 plus a little bit. So in other words, it takes that many radiuses to spin around. Well, how many? Well, it turns out, very convenient fact, that if I have a circle, the circumference of a circle is equal to 2 pi r. So that 2 pi, that's where we get 1 revolution. So 2 pi is 1 revolution. And so we can go back and forth. And in general, we have that 180 degrees is equal to pi radians. Now notice there's no symbol for radians. And in some sense, people like to say, it's sort of like unitless. So this gives you a way to convert. In particular, if I want to go from a degree measurement to a radian measurement, you multiply by pi over 180. And that will do the conversion. All right. Well, let's try some specific angles and see if we can't compute what some of these values are. All right. So, what are some nice angles for us to work with? Let's make a nice chart here. So, we want to do sine, cosine, and tangent. And let's see. We'll put, so we're a little close to the top there. 0. Now, of course, 0 degrees, 0 radians, still the same. All right. So then we'll have pi 6. Now, pi 6 is really 30 degrees. Then pi fourths, 45 degrees. All right. And, okay. Didn't have quite enough space. All right. Pi thirds. That's 60 degrees. And then pi halves, 90 degrees. All right. Good. Good. There we go. All right. So how do we do this? Well, we draw triangles. Let's start with 45, because that's pretty easy. If I draw a 45, 45, 90, that means that these two have the same length. Of course, this is a bad picture, but they're the same length. And so let's just label that 1, Pythagorean theorem. Says this side has to be the square root of 1 squared plus 1 squared, which is 2. So here's our little angle. And now we can just look at the measurements. So opposite over hypotenuse says that the sine is 1 over root 2. Adjacent over hypotenuse, 1 over root 2. Opposite over adjacent, 1. Done. Good. All right. Well, now, what if I wanted something that was 60 degrees? Well, let's start with an equilateral triangle. So then this is 60 degrees, or, because we're doing calculus, pi thirds. And you might say, why do you keep insisting on radians in calculus? And the answer is, it's important for one limit. And what is that? Well, we'll get to that. That's a wonderful topic in calculus. All right. So let's suppose I take it, and then I go straight down. So I'm cutting it in half. Well, if that cuts this length in half, so let's say if the total length were 2, cutting this length in half would mean that this length is 1. So Pythagorean theorem again, I need that 1 plus whatever this is squared has to be 4. So this squared needs to be 3, which means this is square root of 3. So if I want the sine, that's the opposite over the hypotenuse, so that's square root of 3 over 2. Cosine, adjacent over hypotenuse, 1 over 2. Tangent is root 3 over 1. All right, well, what if I want pi 6? Well, now I can use the fact that there's this nice relationship. That this angle, this is in fact pi 6. So we get, if we go through it, opposite over hypotenuse, that's 1/2, adjacent over hypotenuse, root 3/2, and opposite over adjacent, 1 over root 3. All right, well, how about these last two? Well, in some sense, you can think of this as sort of a very flat triangle, where here, there's an angle of 0 at the end. And the hypotenuse is 1, the adjacent side is 1, and the opposite side is 0. So sine of 0 is 0, because it's opposite over hypotenuse. Cosine of 0 is 1, adjacent over hypotenuse, and tangent of 0, opposite over adjacent, is 0. Well, on the other extreme, that would be on this side, pi halves. Well, it would turn out that this would be 1, this would be 0, and then you have 1 over 0, which probably is better to say is infinity. All right, so there's our basic chart. Now, what's the better way to remember this chart? Well, here's how I like to remember sine and cosine. So we're going to go through and just make a really simple chart. So we're going to have 0, pi over 6, pi over 4, pi over 3, and pi over 2. All right, now here's how you do it. This 0 becomes square root of 0 over 2, which is 0, square root of 1 over 2, which is 1/2, square root of 2 over 2, which is 1 over square root of 2, square root of 3 over 2, which of course is square root of 3 over 2, and square root of 4 over 2. So it has that nice pattern. How about cosine? It's just going backwards. Square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, and square root of 0 over 2. And there you go. It's all there. Once you have sine and cosine, tangent, oh, that's a freebie. You don't even have to work hard for that one. You get what you need. All right. Now, what's next? Well, so far, we've really been focused on trigonometry as triangles. But there's another way to think about trigonometry, and that's trigonometry with circles. Well, how does that work? The answer is we start with a circle, but we almost always use a unit circle. So here's a unit circle, and we're thinking this as being centered. And we put our triangle, so our right angle is sitting on the x-axis, and our angle theta is in the corner. It's a unit circle, which means radius is 1. So, how does this work? Well, the opposite side is the y-coordinate of this location. So if I think this as an x comma y. So the opposite side is, the length is y over 1, which means that the y is the sine of theta, and the adjacent side that's the x. And if I take the adjacent over 1, that's the cosine theta. So what really happens is that we can say that the x-coordinate is cosine and the y-coordinate is sine. Cosine theta, sine theta. So this is a really nice way. And the reason I say it's really nice is when we use triangles, it makes sense when our angle is between 0 and 90. But now we can do all sorts of angles. For instance, if I wanted to add to this list, suppose I wanted to do pi. Well, now, where am I at when I'm at pi? Well, the answer is I'm over here, where the cosine is -1, and the sine would be 0, because I'm at height 0. Similarly, if I was at 3 pi halves, which is down there, where would I be? Well, now my x-coordinate is 0, so that says my cosine is 0, and my y-coordinate is -1. So those are some more values we can add. In fact, we can add many, many more to the list. But really, this is about all that you'll need. On another note, this parameterization, it's a really useful parameterization. We'll use it again and again. So whenever we have a circle and we have to describe where are we at, what points are we at, almost always we're going to say, we can describe points on circles by doing cosine theta, sine theta. Well, now that we can talk about cosine and sine for any angle, we can now sort of say, well, what does it look like? What do these functions look like? So let's look at the sine theta function. Well, what happens? So for thinking about sine as we go around, we're at 0, we're going to go up, and then we peak at pi halves, and then we go back down to 0, and then we go negative till we get to 3 pi halves, and then we go back up to 0. So we 0, up, right, here's pi halves, back down, go through, go negative, go back up. So here is at 2 pi, here's at pi, this is at pi halves, this is at 3 pi halves. Now, what happens after 2 pi? And the answer is, after you've gone around 2 pi, you reset. In fact, any multiple 2 pi you go around is always a reset. And so it just copies. Now, whenever you have that kind of, I'm going to reset thing, we have that we're periodic. So trigonometric functions are periodic functions. This is actually a really important thing about trigonometric functions. They're periodic, and so what that means is that we can use these functions to help model behaviors which are periodic. So anything which is periodic, oftentimes we model using trigonometric functions here. Some important things to know is if you look at the sine, it goes between -1 and +1. So sine is always a bounded function. And this can be very useful if we're trying to understand what the behavior of a function is. All right, well, that's just one function. What about other functions, say cosine? What does that do? Well, now we're the x-coordinate. So now when we start, we don't start at 0. The x-coordinate here is at 1. So we're going to start at 1. Then we're going to go down to 0, go more down to -1. So we're going down, and then at pi, we're at -1. And now we're going to go back up to 0, and finally our x-coordinate goes back to 1. So that at 2 pi, we've gone one full revolution. And we're back to where we started, and of course from there we just continue the cycle. Now you might say, these curves look really similar. Just one's a shift to the other. And that's because these curves are really similar. Just one's a shift of the other. So oftentimes, statements which are true about the sine function are also true about the cosine function, just shifted over slightly. A couple of things to note is that sine of theta has symmetry. So sine is an odd function. What does that mean? Well, it means if we plug in negative theta, that's negative sine theta. And cosine theta also has symmetry. It's an even function, which means that cosine of negative theta is the same as cosine theta. So this is really useful when you're working with functions. In fact, sometimes symmetry can give you a lot of information. Now this is, of course, just two of them. Let's talk about another one. Let's talk about tangent, because tangent's going to be very different. It's going to blow up a little bit. Now, we talked about circles. Where does the tangent show up on a circle? And the answer is it shows up in kind of an interesting way. It's the following. If you were to do the following picture, and you just took this line here at 1, and here's your theta, this length right here, that's your tangent of theta. So that's where tangent comes from. So you can imagine that as we're coming in towards that angle of pi halves, we're going to be moving up, 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 which says that tangent should blow up. And if you think about that, well, that's right, because we're dividing by a huge number. A huge number, divided by a small, tiny number, which makes the result huge. So what does tangent do? Well, tangent has a nice property. So we start, tangent of 0 is 0, and then we're going to go up as we approach pi halves. And similarly, we're going to go very far down if we approach negative pi halves. Now from here, it turns out it repeats after every pi. So we get this type of behavior here. That's our tangent function. Now, it's periodic, pi periodic. It's also odd. So tangent is an odd function, which means that tangent of negative theta is negative tangent of theta. Then there's some other things that we can say. But there's one thing I want to look at, which is the inverse tangent. Now, does the tangent have an inverse, strictly speaking? The answer is, strictly speaking, no. Now, the test is draw a horizontal line. And you'll notice it crosses many times. Many crossings means can't have an inverse. But if we restrict to just one part, then we're okay. So we take that curve and we do the inverse. Now, how do you do the inverse? Is you flip it across the line y equals x. So it's going to do that type of motion. And when we do that, we're going to get the following. So what was vertical asymptotes becomes horizontal asymptotes, pi halves and negative pi halves. And now we get a curve that looks like this. So this is called the inverse tangent, also known as arctangent. Now, sometimes you will see arctangent written as tan minus 1 theta. That's a convention. It's not a great convention because some people are tempted to say that tan to the minus 1 theta is 1 over tan theta, which is not correct. So be really careful with your conventions. Now, arctangent is an absolutely beautiful function. It's one of my personal favorites. And if I had to pick one function to have a dinner with, meet a celebrity, I think it'd be the arctangent function. It has beautiful properties. It's a very nice, smooth function. It has a value for all values of your input. Notice tangent doesn't. It has some points where it's not defined, but arctangent's always defined. We can also use some basic facts to say, look, arctangent of 0 is 0, and arctangent of 1 is pi fourths, which is just a way of saying if you take the tangent of pi fourths, you get back to 1. And in some sense, you can say arctangent of infinity, well, that's pi halves. Well, in some sense, that's true. In some sense, that's true. Beautiful function. Beautiful function. I am sure we will run into that function many, many times in our journeys through calculus. All right. Well, as we continue along, let's talk about some identities that are fairly useful. So you have the sum formula for sine. Sine of x plus y. Now you don't need to know this one, but it's a good one to know, and it's one of the ones that we have time. Maybe we'll talk about it at the end. Sine x cosine y plus cosine x sine y. And cosine of x plus y, well, that's cosine of x cosine y minus sine x sine of y. Now, here's a special case. X equals y. So, what does that become? Well, that says sine of x plus x, or sine of 2x, is sine x cosine x plus cosine x sine x. They're the same. So that's 2 sine x cosine x. And cosine of x plus x, that's cosine of 2x. What is that? Cosine x is cosine squared x minus sine squared x. And these are really cool facts. In fact, these are our next 2 out of 6 that we should know. All right, so we definitely need to make sure we know those by heart. But let's go a little bit further. Remember we said cosine squared is related. In fact, cosine squared turns out that's 1 minus sine squared, because cosine squared plus sine squared equals 1 minus sine squared x. So that's another way to say cosine 2x is 1 minus 2 sine squared of x. But of course, we could also have said, hey, we could have said this is cosine squared x, but then I can take sine squared x and say that that's 1 minus cosine squared x. And if we do that, we get that this is 2 cosine squared x minus 1. These are both true. So these are other ways you can write cosine of 2x. Well, why is that useful? Well, one of the things you can now do is you can now say, let's rewrite. So suppose, for instance, I solve for cosine squared x. Well, I could add 1, divide by 2, and I can conclude that cosine squared x is equal to 1 plus cosine 2x over 2. Or I could do it here, sine squared x, where I can subtract 1 divided by negative 2, and if you work that out, you get sine squared x is 1 minus cosine 2x over 2. And these are another 2 of our 6. In fact, now we have all 6 of our 6. We had the sine squared plus cosine squared equals 1. We have these, which we're going to call double angle. So these are our double angle, if you ever hear that referred to. And then these, which we call power reduction. Now, they're pretty descriptive. Double angle says, hey, I have twice an angle. And we want to make sure we can go in both directions. So if you see sine and cosine together, you can say, oh, I can merge that into a single term. Or if you see a cosine 2x, that becomes cosine squared minus sine squared, or vice versa. So it's really good to be able to say, let me mix and match. Let me put things together in a really good way. That becomes useful. Power reduction gets its name because we can reduce the power. See, right now this is a 2. There's no 2 on this term. And so I can simplify the power. Make it something a little bit easier to work with. So, let's see. Maybe we can do a short example that uses our power reduction. Okay, so suppose for a second that I wanted to simplify something that looked like the following. Cosine squared x sine to the 4th x. And by simplify says, look, I'm having a hard time working with higher powers, but just normal trig functions I'm okay with. And we'll see that, in fact, that's something that actually happens. So what can we do? Well, here's something we can do. We can say, look, I can pull off a cosine and a sine. In fact, I can pull them off 2 each, put them together, and then I have a sine squared x. And for the cosine sine, well, I can say that this is 1/2 sine of 2x. So that's why it's nice to look for cosine and sine. Squared, of course, but how about this term? Well, that's sine squared of x. Well, that's going to be 1 minus cosine 2x over 2. And well, what does this become? Well, a half, that's 1/8 sine squared 2x times 1 minus cosine of 2x. And then what can we do next? Well, okay, and well, you keep going, dot, 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 dot. There's work to be done, but power reduction, it's a convenient tool. It's a convenient tool. All right, not the most compelling example, but don't worry, we'll see more. We'll see more. A few more notes I want to talk about. Why do we like Pythagorean theorem? Well, Pythagorean theorem, that is good for distance. And oftentimes we're interested in understanding distances. So, suppose I have a point and another point. And I want to ask, how far apart are they? What's the distance between them? Well, we can construct a right triangle. We can say, well, it's easy to measure the distances on the sides. They're just the change in the coordinates. So I'm putting a little absolute value here just to say, look, it doesn't matter. I could have picked a point down here and it still would have been the same. So we can say that the distance squared, well, that's x1 minus x0 squared plus y1 minus y0 squared. Of course, absolute values don't do anything. And the other thing is, I want just distance, so I take the square root. Square root x1 minus x0 squared plus y1 minus y0 squared. Done. Now, on a side note, here we see the introduction of the square root. The square root is in some sense our nemesis. It's our big challenge to overcome. How do we work with the square root? What do we do? And we'll see in some of our courses that the very thing which caused the square root, which is the Pythagorean theorem, will be also the thing which helps save us. All right. Now we can actually go a little bit further, and we can say, hey, what's a circle? Well, the circle is all the points which are the same distance from a center. So suppose we set x0, y0 is our center. We'll call it hk. That's the center. And I want all the points which are distance r. We'll call that the radius. Well, applying the formula, that says a circle has the form r equals square root x minus h squared plus y minus k squared. In other words, a point's on the circle if and only if it satisfies this relationship, which becomes, of course, squaring both sides, x minus h squared plus y minus k squared equals r squared. So the formula for the circle follows directly from the Pythagorean theorem. All right, a few basic facts about circles we should know. Circumference of a circle is 2 pi r. Now you might wonder, why is that the case? And the answer is definition. Okay, well that's a reasonable thing. That's how pi is defined. Pi is defined as the ratio of the circumference divided by the diameter, which is all the way across, which is twice the radius. The area of a circle, that's pi r squared. How do you get that? Well, here's a fun fact. The area of a triangle is 1/2 base height. Well, that's true. Okay, so what you can do is you can come to this circle and just imagine taking this radius and breaking up into a small number of straight line segments. And then just connecting to the center. So it's almost like you're making a pizza. Very, very tiny slices of pizza. And you can say, okay, well, what's the total area of our pizza slices, which is not exactly the circle because we've cut off a straight line, not a curve on the end. Well, the answer is it's 1/2 base height. So in each of these, the height is the radius. The base is the sum of our distances around here. So our base is approximately our circumference. So the area is 1/2 base, which is something about 2 pi r times the height. And the nice thing is that this about gets more and more close to 2 pi r as we make smaller and smaller slices, which means we go to pi r squared. So it's kind of an amazing fact that this number called pi, which comes from the definition of the circumference, also relates in such a clean way to the area. A few other shapes to be comfortable with are cylinders. And here, cylinder, you have height h, and you have radius r. Volume is pi r squared h, no surprise. And if you have a sphere of radius r, then the volume of that's 4/3 pi r cubed. And that's not so obvious, but you can, once you get far enough along in calculus, actually use calculus to answer that, to show that's true. Okay. Well, I guess for those who stuck to the end, a few proofs. Okay, so let's talk about the Pythagorean theorem. Why is it true? Well, this is a famous theorem, and with almost all famous theorems, there's many proofs. So let's do maybe 1 or 2 proofs. So here's a proof by sort of gluing things together. So we're going to take our triangle A, B, C, and we're going to take 4 copies of it. So here we go. There's copy number 1, A, B, and there's C. Next, I'm going to put A, B, C. So I'm just sort of rotating it and moving it across. Next, A, B, C. And finally, A, B, C. All right, so here's the question. What's the area in this whole shape? Well, first off, it's a big square. So one way to do it is take A plus B and square it, because it's A plus B times A plus B. But the other way to do it is to say, well, look, inside here, this is actually a square. So I'm going to take this square on the inside. That's a C by C squared. So C squared. And I'm going to add to that 4 triangles. In the area of a triangle, that's 1/2 base height. So 1/2 AB. Now we multiply this out. You get A squared plus 2AB plus B squared equals C squared plus 2AB. The 2AB's are the same. And so we can conclude A squared plus B squared is equal to C squared. Done. Done. Now, that's a lovely proof. In fact, there's many variations on this proof of saying, well, let's measure areas in the same way. Let's do something a little different. All right, so let's start with our triangle, and let's just make an observation. Suppose I have my triangle here. All right, so here's A, B, and C. Now, what's the observation? Let's talk about scaling. So we know if we scale, and let's say we scale by a factor of, I don't know, let's call it x for now. The lengths go by x. So in other words, if I have a length 2, and I scale it by x, it's now 2x. The areas, they go up by a factor of x squared. If we had volumes, which we don't, but we might as well say it, they go up by a factor of x cubed. So what can we do? We're going to make 2 observations. First off, let's scale it down. So this is a similar triangle, but this has hypotenuse 1. And let's call this area, we'll give it a name, we'll call it M. So what do we have? Well, We're almost there. One last piece is to say, if I come here and I drop straight down, I can say that this big triangle breaks up into two smaller triangles. And what's true about these two smaller triangles? Well, notice that they have 2 out of the 3 angles which match, which means all 3 angles match. So these two small triangles are actually similar to the original triangle. So let's figure out the areas. So this one right here, that's the hypotenuse of A. So to scale 1 to get to A, I scale up by a factor A. So in other words, x equals A. So we have that this small piece of area here is MA squared, because I multiply the area by how much I go up by. This one, the hypotenuse is B. Again, it's similar. So that area is MB squared. And for the whole triangle, I have to scale by a factor of C, which gives us MC squared. And now, well, let's cancel the m's. A squared plus B squared equals C squared. I first learned this proof many years ago from a professor, really good professor. And of course, the joke is that this is Einstein's proof. Well, I don't think really Einstein came up with it. But the fact that you see MC squared, well, different kind of MC squared. So, all right. So there you go. A proof of the Pythagorean theorem. Okay. And now for the really die-hard people. All right. One thing you might want to know is how can you prove those formulas for sums of angles? So suppose we come here. Let's draw ourselves a picture. Let's say that this here is a triangle, right triangle with angle x. And now, remember, we can always scale things. I'm now going to come off this and put another right triangle here. And there's angle y. And up here, I'm just going to put a triangle. Okay. So let's see if we can figure out what's true. Well, one thing that we can figure out here is the following. This angle is complementary to this angle. In other words, if you add these two angles together, they'd add up to 90 degrees, or a right angle. Notice that these two angles are also complementary to each other, because there's a 180 here, but there's a right angle already taken out, which means that this angle here has to match that angle there. All right, that's one thing we're going to need. All right. One other small thing we'll need is the following fact. And this is actually really easy to see if you go back to our definitions, which is suppose you know an angle theta and you know the hypotenuse. Let's call it T. It doesn't really matter, we just need a name. Then, if I know the hypotenuse, I can actually determine these sides. Let's do this side. So this is the opposite side. So what we have, we'll call it question mark for a second. What relates the opposite in the hypotenuse? And the answer is the sine. So sine of theta is the opposite over the hypotenuse, or what we get here, let's see, sine of theta is opposite over hypotenuse. Yep, opposite over hypotenuse. So we can get that the question mark is T sine theta. So that's T sine theta. Similarly, if we come down to this one, same process, T cosine theta. All right, now we have everything that we need and to figure this out. Let's say that this length here is 1. And again, we can always scale, so we make it true. So we're going to apply this rule, and that says that this length on this side right here, well, that's the adjacent to y, so that'll be cosine of y. This length is opposite y, so this will be sine of y. Okay, well, that's good. So essentially what we're doing is we're using this hypotenuse to figure out those two sides. Now we're going to repeat this process. So let's come to this triangle. Here I have an x, there's our sine of y, so this is now my length t. And I'm going to multiply that to get this side, since it's adjacent, by the cosine. So it's sine y, which is the length of the hypotenuse, cosine of x. Over the opposite side, be sine y, sine x. So that we get these two pieces coming in. Similar process happens here. What we'll get is that this bottom length, the whole length across, cosine y, cosine x, and this side length over here, which is opposite x, is going to be cosine y, sine x. Now, last two things to do, and we're done after this. Suppose I wanted to know this angle. Well, I can look at this triangle. So this whole length here would be, according to our rule, because this is 1, so this would be the sine of the angle x plus y. So this length is sine of x plus y. Well, it's going to be this length plus this length. So that's going to be sine of y, cosine of x, plus cosine of y, sine of x. Now, how do I get the cosine? Well, that's this length down here. So cosine of x plus y. Well, how do we find that? We take the whole length across, cosine y, cosine x, but then we subtract off this little piece. That part we don't need. Minus sine y, sine x. And there you go. Good. It's nice to know why things are true. It's not just enough to know things are true, but it's nice to know why things are true. And then we're more likely to use them correctly. Knowledge is power. Let's use it wisely. Good.